In this video, we are going to derive a simplified model for a resonant wireless power transfer system. The resonant wireless power transfer system essentially employs the resonance standard for power transfer. Also, this standard is called Alliance for Wireless Power Standard, or A4WP. And in this standard, the power is transferred via a frequency equal to 6.78 megahertz. And the amount of power that can be transferred is up to 70 watts. Of course, this standard goes through updates annually, so these numbers are rough numbers essentially. As for the coil orientation, so for wireless power transfer, we have a primary coil and a receiving coil or secondary coil. And power is essentially a magnetic field is coupled between both, and so power is transferred from primary to secondary or from the transmitter to the receiving side. So typically in other wireless power transfer standards, the coils essentially rely on inductive coupling between two coils. So the two coils have to be tightly coupled or placed very close to each other, and their orientation should be perfect so that the maximum amount of power is transferred from the primary to the secondary. On the other hand, in resonant wireless power transfer, the coils can be any orientation and any placement, and it relies on magnetic resonance or essential resonance in order to transfer power between the primary to the secondary, not just the inductive coupling between two tightly coupled inductors. And sometimes the transmitting circuit, or usually the transmitting circuit and receiving circuit, they need to establish communication to determine either feedback or the amount of power to be transferred or other issues related to the wireless power transfer. And this is done in this standard using Bluetooth, low power Bluetooth. So first of all, to find a simplified model for the wireless power transfer system, the first thing we need to model is essentially the primary and secondary coil and the coupling that's happening between them. So in this case, as a first order model, in a future video, we are going to see a more detailed model for the transformer essentially. But for now, we'll just assume, or as a simplified model for the transformer can be modeled as a coil or an inductor in series with an ideal transformer. Okay, and this ideal transformer, can be of any ratio, N to M ratio. Now, there is a small issue. If this is essentially the link we have that we need to transfer power from the primary side to the secondary side, how we are going to do that? Assume we have a 10 ohm resistive load that we need to power from the primary side essentially. So one way to do that is just put an AC source, a sinusoidal source, say its amplitude is 1 volt, and we put it at a frequency equal to 6.78 megahertz, given that the channels that we can use is 6.78 megahertz in this standard for power transfer. And we face a small issue in this case, and basically the inductor is going to choke the amount of power that we can transfer, or limit the amount of power that we can transfer to the 10 ohm resistor. To see that, let's assume for simplicity that the ideal transformer that we have, has a turns ratio 1:1. And then we have a 10 ohm resistor. We have an inductor equal to 10 microhenry. We have an AC source, 1 volt at 6.78 mega. Now, we studied before that if you have a 10 ohm resistor at the secondary side, you can transfer it to the primary side according to the turns ratio squared. So in this case, it's 1:1, so essentially this 10 ohm resistor can be transferred to the primary side as 10 ohm resistor. And then we have the 10 microhenry, and then we have the AC source, 1 volt, 6.78 mega. Now, if we calculate the impedance or reactance of this 10 microhenry, what is going to be? Well, omega L is equal to 2 pi times 6.78 mega. That's the frequency times the inductance 10 microhenry. So this will be equal to approximately 426 ohms. So the equivalent reactance is 426 ohm. And now, what is the amount of voltage that will appear, or the amplitude of the voltage across the 10 ohm? Well, that's very simple. We can use voltage divider. We have a 1 volt source, say the phase angle is 0 in complex representation, 0 degrees, and then it's multiplied by the 10 ohm resistor, that's the load that we want to deliver the power to, divided by 10 ohm plus J 426. So if we are interested in the amplitude of the voltage across the 10 ohm, this is going to be basically 1 times 10 divided by square root 10 square plus 426 square. Okay. And so this will be essentially equal to 0.024 approximately volts in amplitude. And so the power that's delivered to the 10 ohm resistor is going to be the amplitude, which is 0.24 square, divided by the 10 ohm resistor. While the source is 1 volt, so the remaining amount of voltage is essentially appears or drops across the inductor. And only 2.4% of the applied voltage shows across the 10 ohm resistor to deliver or to power the load resistor. Okay, and the remaining amount, which is about 97% of the voltage, is essentially dropped across the 10 microhenry or the equivalent inductance of the transformer. Okay, and that's the problem with this inductance. We need to get rid of this inductance at 6.78 megahertz. So what we're going to do is we connect a capacitor in series with the primary side coil, so that we tune out this inductance. So essentially, the negative reactance of the capacitor is going to cancel the positive reactance of the inductor at 6.78 megahertz. And this way, we don't have voltage drop across this inductance or the equivalent inductance of the transformer at the operating frequency of 6.78 megahertz. And all of the applied voltage can appear across the 10 ohm. So instead of 2.4% of the voltage appears across the 10 ohm, essentially we find that all of the input voltage amplitude appears across the 10 ohm. So we connect the capacitor in series with the inductor, and then since the ideal transformer is 1-to-1, we can just move the load to the primary side, 10 ohm, and then we have the AC source. And now, since as I mentioned, the capacitance, the negative reactance of the capacitor will cancel the inductance, the positive reactance of the inductor at 6.78 megahertz, and we end up with a short circuit. So both are cancelled at the operating frequency, and all of the input voltage 1 volt appears across the 10 ohm, and we can transfer the amount of power that we like. Okay, so the first thing, in order to transfer power via the inductive channel or the transformer, essentially, which we model it for now, for simplicity, as an inductor in series with an ideal transformer, the first step is to connect a capacitor in series with the primary coil so that we tune out the equivalent inductance of the transformer. okay, and enable all of the input voltage to be applied all across the load essentially. Then, as we mentioned before, essentially we had a transmitter, we have a half bridge, and this half bridge produces a square voltage. And this square voltage includes a fundamental component at 6.78 megahertz, as well as higher order harmonics at the odd harmonics, the third, fifth, seventh, and so on. And so, since we have a capacitor in series with the equivalent inductance of the transformer, then we have an ideal transformer. Say essentially it's 1-to-1, 10 ohm resistor. The half bridge essentially produces a square voltage. And so essentially this series resonant tank is going to extract only the fundamental component at 6.78 megahertz and reject the remaining harmonics. Okay. And then after that, now the voltage that we receive here at the secondary side is going to be sinusoidal. However, we need to say charge the battery in the phone, right? Or whatever application this wireless power transfer system is used to power essentially. So what we are going to do is we're going to use a full bridge rectifier in order to transform the AC voltage and current into a DC voltage and current. So we'll have our system here. The capacitor in series with the inductor, the half bridge produces a square voltage, as I mentioned. And then we have the transformer. This transformer essentially will go to a full bridge rectifier. This is the ground of the DC load. And then essentially this full bridge rectifier will take the AC voltage and current of the secondary side of the transformer or the inductive channel essentially, and transfer it into DC voltage and current. So we need a low pass filter, an RC filter. So we have the capacitor in order to filter out that essentially the full bridge rectifier is going to transform the sinusoidal voltage and current into or the bipolar voltage and current into a unipolar, so it's in the same direction. And then we use a capacitor so that it establishes a low pass filter, and we take the average value of the generated current and voltage, a unipolar to take the DC component of the generated unipolar voltage and current. And then we have the load resistor, whatever 10 ohm or whatever load we are interested to power. Now, as I mentioned, assuming a 1-to-1 transformer, this means that the current at the secondary I2 will be essentially the current at the primary, right? Because the turns ratio is 1-to-1. And the voltage at the primary will be essentially equal to the voltage at the secondary, given the turns ratio. So V2 is equal to V1. I2 is equal to I1. So essentially we can just remove this transform, and we can model the system as a half bridge that's powered from a DC input voltage. Then we have the resonating capacitor, and then the primary coil, as we said, the inductive channel essentially can be represented by a large coil in series with a transformer. And since the transformer is 1-to-1, we can just remove it because essentially it forces the same voltage on both sides and the same current on both sides, so we can just remove it from the circuit. And then we basically can simplify. We have the full bridge here. The filtering capacitor C, and then the DC load R. That's basically the output DC voltage across the load. And of course we have here as you can see, we have the ground of the secondary side, because essentially the transformer separates this ground from the other ground, from the DC load ground essentially. And so basically here I'm using two symbols. This is the transmitter side ground, and this upside down triangle is the ground, the symbol for the ground on the secondary side.